Good morning, everyone. Well, Jackie has given quite a bit of good introduction of me and the topic I'm going to talk about. So I will start with the topic itself. As we all know, quenching and distortion go hand in hand. They are inseparable, but there are some ways by which distortion can be minimized, and one such way is by quenching in molten salt. The distortion in quenching is two types: size distortion, shape distortion, and they both occur simultaneously and they have distinct influence on the final outcome as far as distortion is concerned. Size distortion is due to the volumetric expansion that takes place during the martensitic transformation. It is a natural phenomena having some degree of predictability, and it is mainly affected by the steel composition and the quenching process itself. Shape distortion, also known as gross non-symmetrical distortion, it is primarily caused by non-uniform stress conditions created by thermal, mechanical, and possibly by material differences. It's mainly influenced by part design, non-uniform heating, non-uniform quenching, and the quenchant itself. It is less predictable than the size distortion. Now let's look at the conventional quenching. This is TTT diagram with cooling curve superimposed on that. And this is martensitic transformation zone. And this is temperature versus time. During quenching, the surface obviously cools faster than the center. So what happens? The surface transformation takes place first, and the surface expands first. And then later on, it's the core that transforms into martensite, and that expands. And this creates a stress on an already expanded surface. Let's take a look at some of the points. So because of the core expanding after the surface has already expanded, there is a distortion. And this distortion may be within the tolerable limits on low hardenability steel and in low section thickness. But as the hardenability and the section thickness increases, distortion also increases. And it may reach to the point, to unacceptable distortion, or it may even cause cracking. And this can be overcome to a large extent by interrupted quenching, and we'll talk about that. Interrupted quenching is where you interrupt the quenching process at a temperature which is slightly above MS, that is martensite start temperature, and you allow the entire cross section to equalize in temperature and then cool it to room temperature, during which the transformation will take place on the entire cross section almost simultaneously. So the volumetric expansion in the entire cross section will take place almost same time. So this minimizes distortion. And there are various processes of interrupted quenching, and I will be talking about Martempering, Austempering, and various their variations. In interrupted quenching, this is shown here schematically. You interrupt the quenching at a temperature just above MS temperature, where surface and the center come to the same temperature, and then you allow the transformation to take place. What could be the medium to interrupt the quenching? As we know, most of the steel have MS temperature 350 degree or, sorry, I keep pressing the wrong button. Yeah. MS temperature for most of the steel is in the range of 350 to 700 degree F, which means water, brine, polymer, and most of the oils cannot be used. This leaves molten salt as the natural and the practical choice. Molten salt has been the quenchant of choice for decades for interrupted quenching processes. It helps in controlling and minimizing both types of distortion we talked about. And I consider that as an ideal quenchant for interrupted quenching processes. And we'll go into the details of this process. But first I want to say a little bit about the salt itself. Quenching salt is a mixture of nitrates and nitrites of sodium and potassium. There are nearly a dozen different compositions available, and they mainly vary in their melting points, which may be from 275 to 500 degree F. But once they are in molten state, they all exhibit nearly the same physical property at the same temperature. And these are the physical properties, and I'm not going to go into details. These are just the numbers. Let's look at the uniqueness of the molten salt as a quenching medium. It has a very wide operating temperature range from 300 to 1100 degrees F. There is no vapor or boiling stage of quenching commonly encountered in all other liquid quenchants. So heat extraction takes place primarily by convection stage and usually at a uniform rate. And this helps in minimizing distortion, and its quenching severity can be controlled or adjusted by varying temperature, agitation, and water content if water is added. It does not pose any fire hazard. It's not a combustible material. It has excellent thermal and physical stability, and it's easy to wash and recover for reuse. It does have limitations, and obviously one of the limitations is you have to use it above its melting point, so you can't use it at lower than the melting point. And combustible and incompatible material should be kept away from the salt from safety point of view. And it does require adequate safety precautions, mainly because of the temperature. But most of the safety concerns have been addressed by the advances in molten salt equipment. So they are no longer considered as deterrent for the use of salt bath quenching. This is the cooling curve for molten salt at 495 degrees temperature versus time, and this is the cooling rate versus temperature. Operational variables are temperature, agitation, water content, residence time, and there are other factors like steel composition, section thickness, austenitizing temperature, configuration of parts. But these are not strictly an operational variable, but they do affect the final output. Temperature, lower the temperature, greater is the quenching severity. Its effect is marginal compared to agitation and water content, but it can be manipulated for some remarkable results. And we'll go into some of the examples. Agitation, it has greater effect than temperature as a variable. It also can be manipulated, and it is best achieved by propeller type of agitator. And agitation must be on when water additions are made in molten salt. Here is the cooling curve with the effect of agitation this is the average cooling rate from 1200 to 500 degree F. It is calculated based on the cooling curve. And here is the flow rate in centimeter per second. And as the agitation increases, so does the cooling rate. Water content, as I mentioned, agitation should be kept on from safety point of view. It increases quenching severity significantly. A normal range of water content is 0.5 to 2%, depending on the operating temperature. And it can be used in the range of 300 to 500 degree F. At higher temperatures, the solubility of water in salt decreases significantly. At 600, I think it's maybe 0.25% or something like that. And with the combination of agitation and water content, the quenching severity can increase by 3-fold compared to salt that does not have water and it is not agitated. And other fringe benefits of adding water is it lowers the freezing point or melting point of the salt. So it gives you a little more expansion of operational limit. And you can use wash water or steam instead of using direct water to conserve salt or energy. Now here is a cooling rate versus water content, and this is obviously with agitation. Let's look at the process called Martempering. This is the same slide we talked earlier. The quenching is interrupted at temperature slightly above MS temperature, and then the components are allowed to air cool or water cool, and then you naturally carry out the tempering process. In Martempering, the salt temperature is usually in 350 to 500 degree F range, depending on the type of the steel. And the duration, that means how long you keep in the salt bath, is usually few minutes depending on the section thickness and the quenching severity. It's applicable to carbon steel, low alloy steel, gray cast iron, etc. And the section thickness up to 1 inch can be martempered depending upon the hardenability of the steel. As an example, martempering of bearing rest, I have given one example here where martempering is carried out at 450 degree F for 2.5 minutes, and there was a considerable reduction in distortion. And in this particular case, the customer switched from oil to salt, and he was able to reduce the grinding time that is needed for corrective size from 50 minutes to 7 minutes. So that gives you a magnitude of how much distortion has decreased. Another example is martempering of piston ring made of cast iron. In this particular case, it was martempered at 480 degree for 4 minutes, and by switching from polymer to salt, the distortion was reduced by nearly half. Another variation of martempering is carbomartempering. As the name indicates, it's performed after carburizing or carbonitriding. So it combines the benefit of both the processes. The temperature is somewhere between the MS temperature of case and MS temperature of core, and it provides tougher than carburized and conventionally quenched parts. There is minimum distortion because there is less case to build up because minimum distortion, and less to grind after hardening is done. An example of Carbomartempering of Sun Gears. Here, distortion was so negligible that in many cases gears are fitted without doing any corrective grinding. Another example or variation of Martempering is modified Martempering. The modification is in the salt bath temperature. It is kept slightly below the MS temperature, and this allows for low hardenability or thicker section to avoid intersecting this pearlitic nose here and still be able to do Martempering. So it is applicable to more variety of steel than the conventional Martempering. Martempering can also be done using two baths. For example, this is an example of steel balls made of 50 to 100 steel, where they are first quenched in water or brine for a very short time, just some seconds, 10, 20 seconds. And then they are immediately transferred into a salt bath. And this helps in avoiding the pearlitic nose of the TTT diagram. And it helps in increasing the depth of hardening, and it's useful for thicker sections. Another variation of Martempering is when mechanical straightening is carried out. There are some parts that require straightening after heat treating is done. And if you have completed quenching and tempering, then doing this straightening is very difficult and sometimes impossible without breaking the part. So what is done here is the straightening is done just before the MS temperature, when the microstructure is still austenitic and it is soft, so you can carry out the mechanical straightening. And the examples of this include simple and complex shapes made of hot work die steel and some martensitic stainless steel. Let us look at Austempering process. This is a conventional Austempering where the cooling curve comes down here and the parts are held at a temperature above MS temperature, and they are kept at that temperature long enough so that transformation proceeds in this direction and not into martensitic direction. This is the benitic zone. So it forms the microstructure known as benite. Let's look at some more details. Obviously, duration would be few minutes to few hours depending upon the TTT diagram, just long enough for the transformation to be complete from austenite to benite. The materials that can be austempered are carbon steel with 1% manganese, low alloy steel, ductile, and gray cast iron. Advantage of Austempering: many of them are same as Martempering. The microstructure formed here is benite, so the difference between the two processes would be the properties of benite versus the properties of martensite. Benite has slightly lower hardness, but it is much more ductile, and it does not require any tempering that is required after martensitic transformation. And there is lower distortion. As a result, it has it's tougher and more wear resistance. And it also has higher impact and fatigue strength compared to Martempered components. Applications of Austempering: seat belt hardware, particularly the seat belt components made of, this is an example, AISI 1055 steel. They are austempered at 680 to 700 degree F for about 8 minutes. And here the auto industry safety requirement is that this component must bend but must not break during any impact shock load, in other words, in any accident, because that would be more disastrous. I want to make a specific mention of ADI, Austempered ductile iron. It's usually done in 500 to 700 degree F, anywhere for half an hour to 4 hours duration. And the microstructure here is osphierite, not bainite, that is for steel. It has excellent combination of strength, toughness, and ductility. And in general, it outperforms quench and tempered ductile iron components. The application includes gears, hubs, kingpins, and so on. One variation of Austempering is Carboaustempering. As the name suggests, it's carried out after the components are carburized. Here, the core becomes hard first, and then the case becomes hard. So this helps in minimizing distortion, because expansion starts at the core and then it progresses towards the surface. The core may be martensitic or bainitic depending upon the steel composition and the quench severity, but the case is essentially bainitic. It provides excellent fatigue strength and wear resistance, and it is superior to carburized and conventionally quenched part. Applications of Carboaustempering: various types of gears and automotive components. And as an example, premature failure of carburized and oil quenched pinion gear was prevented by switching to Carboaustempering, because it provided greater ductility in case, and it also increased the compressive stresses at the surface. Let's look at a modified Austempering. What it is, the cooling curve is intentionally allowed to intersect this paralytic nose of TTT diagram, and then it continues further down. So this is a modified practice of Austempering. The microstructure is consisting of a mixture of bainite and perlite, because the cooling curve is intersecting the paralytic nose. So the hardness is relatively low, but the ductility is extremely high, and the steel tensile strength is also moderately high. And one of the excellent example of modified Austempering is wire patterning. We can also combine the two processes, Martempering and Austempering, to take the benefits of both, that is martensite and bainite. The parts are first quenched in an Austempering bath for half the normal Austempering time, and then they are cooled to room temperature. So you essentially get the mixture of martensite and bainite. The hardness of martensite gives the benefit, and the toughness of bainite also adds as a benefit. And by various time and temperature cycles, you can develop various ranges of hardness and toughness for a particular steel. Austempering can also be done with two salt bath. It helps particularly for low hardenability steel. The first bath is kept just slightly above the MS temperature, but the second bath is at its normal operating temperature. As an example, it can be done on 1080 steel parts, where the first bath is at 500 degree temperature and the second bath is at 600 degrees temperature. Austempering with manipulation of agitation. Here the example is thin-walled cylinder liners, where agitation is intentionally kept off for the first 15 to 20 seconds to minimize the thermal shock. It is then turned on automatically to complete the Austempering operation. This helps in minimizing distortion without any sacrifice in the required mechanical properties. And the example I already mentioned. In summary, as I mentioned, we covered nearly 12 different processes that are possible with salt bath quenching, and they all help in controlling distortion and achieving the desired properties. Now there are automated and programmable equipment features available for salt bath quenching that makes it fast and economically attractive. As a result, application of Martempering, Austempering, and their numerous modifications continue to grow. And I want to mention at this point that I presented the same paper last month at the International Conference on Quenching and Distortion Control that was held in Chicago. I thank you for your attention. I will be available for any questions.